In these three examples, we're going to look at something sliding down an inclined plane. We're going to look at it without friction, and then two examples with friction, one at a constant velocity, one with acceleration, to kind of tie everything we've done so far all together. So this is example 5.6 out of your book. We have a toboggan or a sled that's sliding downhill. The hill makes some angle alpha. And they put a bunch of little people in it. I'm just going to put one little person in it. They're sitting in there. And this whole weight of a toboggan and passenger has a weight W. There's no friction. We want to find an expression for the acceleration, and we want to find an expression for the normal force. Obviously, the very first thing we're going to need is to draw that free body diagram. It's going to help me know how to set this up. The object has weight that comes straight down, and there's no friction. There is a normal force. The normal force, of course, is going to be pointing perpendicular to the surface. So the normal force points at an angle like this. Now, I think I want to move that dotted line because I think I want to use since the object's going to be moving down the ramp, I want to have my frame of reference like that. I want this to be my x-axis, and I want this to be on my y-axis. This would be my negative x. This would be the negative y. So we can see there's actually only one force. We only have two forces. We've got gravity, which is actually what's going to cause it to accelerate down the ramp or down the hill. This is supposed to be an icy hill with no friction. And we have the normal force, which helps press back against the sled. It's a support force. All right. We have to take the force that's not on the XY axis and get components. We've already done this. Anytime we are on an inclined plane, the horizontal component of the weight is simply W sine alpha. Now remember, this is that unusual circumstance where to get the x, we use sine alpha, and that's because the angle is not really being measured from the positive x-axis. Wy is W cosine alpha. Now, as soon as I do that, I can redraw this picture. And I'm going to put my new vectors that weren't on the original. There's Wx, and there's Wy. Right away, it's really easy to see that the normal force has to equal Wy, so that's one of our answers. Which is going to be mg cosine alpha. I did go ahead and replace, I could have left this as W cosine alpha. It wouldn't make any difference. If we know the weight, we know the weight. Really, there's no reason to put mg there on this part, but there's going to be on the second part. All right, what about acceleration? Well, you can see that there's no friction, so there's nothing opposing Wx. So if we go with the net force equals mass times acceleration, well, the net force is Wx, or W sine alpha equals mass times acceleration. But remember, W is mg. So those masses will divide out when I divide by mass. So I end up getting that my acceleration is simply g sine alpha. Let's stop and think about this, because I think it makes a lot of sense once you see it. First of all, the acceleration doesn't depend on your mass. But that's always true when something is accelerating due to gravity. If I draw this hairbrush, its acceleration doesn't depend on its mass. It falls with the same acceleration as this pencil pouch. I sit here and draw up all kinds of things, and they all accelerate at about 9.8 meters per second squared. When you accelerate down something like an icy hill, how much of your weight, in free fall, all of your weight makes you accelerate. But when you're on a ramp, only the part that makes you accelerate is this Wx. This causes your acceleration. It doesn't depend on your mass. It does depend on the angle. If I let the angle be 0, sine of 0 is 0. Your acceleration would be g. You would be in free fall. I'm sorry, sine of 0 is 0. That would be a horizontal surface, and you wouldn't accelerate at all. If you were at rest on a horizontal surface, you don't slide down the hill. You just sit there. If I let this go all the way to 90 degrees, sine of 90 is 1, and then you'd be in free fall. Picture that. If you took this slope and you tilted it till it was straight up, that'd be free fall, and you wouldn't have a normal force at all. So these answers make really good sense. When you're sliding down a hill, you slide down because of that horizontal component of your weight. Okay. That one we didn't have any friction. We want to add in some friction, same picture, but we got to put a little more stuff in. Friction always opposes motion. So now we have this frictional force. We still have the same horizontal and vertical components of the weight. The only thing now is we've got this extra, okay? The normal forces hasn't changed at all. They want us to find this, they tell us for this problem that we have a coefficient of friction that we're going to call UK. So this relationship between the hill, it's not perfectly smooth ice, there is some friction. So our frictional force is mu k times the normal force. But I already know that the normal force is the same as Wy. So this frictional force is mu k times the normal force, which is W cosine alpha, or I'm going to put mg cosine alpha. That's my frictional force. Okay, the question asks, for what angle will the slide move at a constant speed? For what angle will the toboggan slide with a constant speed? Well, it's going to slide with a constant speed when Wx and the friction force equal each other. That's what we're getting out of this picture. We can tell, oh, constant speed, these two have to be equal. I need Wx to equal the friction force. I need W sine, I'm going to put mg, don't know if that's going to be important or not, mg sine alpha has to equal mu k mg cosine alpha. Oh, this is actually very nice. The mg's cancel out. I could have left them as w's. And I get mu k has to equal sine alpha over cosine alpha. Hopefully you guys remember your trig and that sine over cosine is tangent. So I get mu k has to equal tangent alpha, or alpha has to equal the tangent inverse of the coefficient of friction. It makes sense if we stop and think about the angle is going to depend on how much friction there is to move at a constant speed. The less friction there is, the lower that angle is going to need to be to keep you moving at a can. Because as you increase the angle, you tend to go faster. So if you increase the angle, you tend to go faster. It's going to take a higher amount of friction to keep you moving at a constant speed. So as this number gets larger and larger, this angle will also get larger and larger. All right, we're going to do one more. We're going to keep the same picture. The difference now is we're going to accelerate. I should have taken that out because we had friction on that last one. All right. See if we can go to a steeper hill so we know we're accelerating. Now that example I just figured was 511. So I did 511, now I'm going all the way to 512. We have a steeper hill with friction, and we're asked to find the acceleration. So we're not moving, we're not at the angle that gives us a constant velocity anymore. We're at a steeper angle than that, but our picture hasn't really changed. We have these, we know Wx was mg sine alpha. We know that Wy was mg cosine alpha. We know the frictional force is mu k times the normal force. Well, mu k times the normal force, look at your picture. Your normal force has to equal Wy. So it's mu k times mg cosine alpha. I put the m's in this one because I know how I'm going to have to solve this problem. The net force has to equal the mass times the acceleration. Now, there is no acceleration vertically. These two are equal. So our net force is just going to be Wx minus friction has to equal mass times acceleration. mg sine alpha, that's Wx, minus the friction, mu k mg cosine alpha equals ma. To solve this for the acceleration, the only thing that I have to do is divide by m. But I think I'm going to go ahead and factor out the g. Look at this answer and let's stop and think if it makes sense. When we did not have friction, the acceleration, if this mu k is 0 and there's no friction, the very first example, our acceleration is g sine alpha. That's what we got. Now, if this acceleration is 0, we can rearrange this and set that equal to 0, and we will get that mu k, we could solve for mu k, and we would find out that mu k has to equal the tangent inverse, the tangent of alpha. Mu k is equal to the tangent of alpha, or the angle alpha would have to solve to equal the tangent inverse of mu k. This supports our previous two answers. This is the most general case of all. The others were a little more specific. I just thought it would be good to work through these together. I know they're not easy because they don't have numbers, but that's one of the skills we kind of have to get used to, is how can we work a problem and just get an expression, and then later we could come in. If you told me what the angle was, I could plug in the angle. If you told me the coefficient of friction, I can plug in the coefficient, and I can solve it for lots of problems. All right, that's the end of this video.